more energy to listen to my talk. My name is Simon Keizer. I'm a research engineer at Toshiba Europe, the Cambridge Research Lab. I'm part of a small team of 7 people at the moment working on speech technology. And within that group, there's 4 people working specifically on spoken dialogue systems. So our lab is very research-oriented, so we're quite far from product deployment, but hopefully our ideas in technology will eventually feed into the business of Toshiba. So introduction, conversational AI, as we see it, is technology enabling users to interact with a machine using natural conversation. The conversation can be speech, it can be text, it can also be multimodal, in particular in the context of human-robot interaction, where we also have situated interaction. That is, the dialogue participants, they share a space and a physical space, and they can refer to that space as well. So applications vary from simple information navigation, like searching for restaurants, which are our favorite toy application. It can involve recommendation by the system, but you can also imagine searching through a catalog of products where the system makes recommendation, and eventually the user could choose a product and a transaction can happen, the user buying that product. But there's also other kinds of applications. One we are now currently starting to look at is in the context of human-robot interaction. For example, instruction giving, following. And there's other application areas like tutoring. And in the past, I've also worked on negotiation dialogue. So to set the stage of this bit of research that we've carried out last year that I wanted to discuss today, I want to go through a typical architecture. You've already seen something very similar in the previous talk. This is a kind of simple pipeline architecture which shows you the different aspects that any dialogue system should have. So you have speech recognition going from the speech of the user to text. In some form or other, you have some form of natural language understanding component which produces the meaning of the utterance. We usually use the term dialogue acts in this case. Some of you may speak rather in terms of intents and entities, but this is a more general concept. Then we have the general, the central component of the system, the dialogue manager, consisting of 2 parts. One is updating the overall state, or the state of the overall conversation, taking into account everything that's been said so far, including the last user utterance. And then there is this action selection component, which decides, based on the current state of the conversation, what's the most appropriate thing to do as a system response. This again takes the form of something like dialogue acts, and eventually this leads to the system's response utterance. So there's been many different approaches to building spoken dialogue systems. The traditional way is a very modular approach where you have different components that can be developed more or less independently. This kind of ties into the ideas of plug and play and interoperability, and also allows you a degree of transparency, and this links to explainable AI as well. Of course, with the deep learning wave, more end-to-end solutions have become more appealing, with the very clear advantage of reduced need for annotations, for example, dialogue act annotations. If you can skip them, that would be cheaper, of course. It also avoids downstream error propagation, and very recently, of course, we've seen the emergence of the large pre-trained language models, which can be used to fine-tune a model for a specific NLP or dialogue task with relatively little training data. So if you go back to the architecture, you can imagine combining speech recognition with language understanding. So you go directly from speech to the meaning representation without having to do the actual transcription task. Or you can combine natural language understanding with state tracking, going from the user utterance directly to the updated state. And an even more radical approach would be a complete end-to-end solution with user text in, system text out, and a big black box in between. So, oops, I went slightly too far. So even though we have also already started using the large pre-trained language models in our model, there is still a big discussion about how useful they are and what they can, what their limitations are. For example, conversational speech phenomena such as turn taking and grounding are not really captured at the moment, just yet. And also we're tackling with the problem that generative models like GPT, they can produce, they can sometimes spout nonsense, right? It's the infamous hallucination problem. So we are still taking kind of the modular approach as shown in the pipeline architecture. And so the motivation of this particular work is given by, so we're taking a data-driven approach. So we do believe that statistical spoken dialogue systems are more scalable than using rules. So we want to replace the rules with trainable models. But the problem here is that the early statistical models still rely on in-domain annotated data. So if we want to build a dialogue system for a new application, we need data for that application. So that's exactly what we're trying to address in this particular work. So to address this problem, transfer learning techniques have been tried out, and they work to some extent, but they kind of only work to the extent that the source and target scenarios are very similar. So the application that you start with is very similar to the new application. And so we wanted to be able to build dialogue systems for our new applications that can be very different in nature. In order to do that, we look at multidimensional dialogue modeling. So I've already, in academia, worked on this kind of modeling in the past with Professor Harry Bunt. And so that will be the basis for our transfer learning methodology, because this multidimensionality allows us to have a clear separation between task-independent aspects and task-specific aspects of dialogue. So what is this multidimensionality in dialogue? So we believe that dialogue participants, they address multiple aspects of communication or dimensions of communication simultaneously when they produce utterances. So we distinguish between the task or activity itself, like restaurant search or instructing a robot to do something. And we distinguish that from aspects that are generic to any conversation in whatever scenario you're working in. We call that dialogue control. That subdivides into what we call feedback, which is about the participants trying to make sure they understand each other and reach common ground, which further subdivides into auto-feedback, which is about the speaker's processing, and allo-feedback, which addresses the addressee's processing of your own previous utterances. And then there are additional interaction management dimensions like turn-taking, time management, and also the social aspect of conversations. So these include things like greetings and thank you and apology. So the dimensions indicated in red here are the ones that we currently support in our dialogue system. So going back to the architecture, we focus our work on the central component, so the dialogue manager, and in particular the action selection. So zooming further in, a typical dialogue system would have an action selection component driven by a single policy. So you have one model that in a given context chooses an action from a fixed set of possible actions. What we propose is a system with multiple policies. So we'd have separate policies for the task, feedback, and social dimensions, and an additional evaluation that looks at the output of each of these policies. So these are candidates, and decides, okay, this combination of actions that eventually is going to lead to the system response. So in this case, you could combine the offering a restaurant from the task dimension with an implicit confirmation saying you understood that the user wants Italian food. This is kind of the mechanism. And the main advantage here is that you have a separation of these application-independent policies, feedback and social, which are therefore transferable, and two application-specific non-transferable policies that you would have to train from scratch for any application. So this shows you some example of the some example actions for the different policies. So you have for task, you would have offer a restaurant or request a preference from the user, for example. For feedback, you have things like these clarification questions, right? Here you have implicit confirm and explicit confirm, things like that. And for social, we have accept thanking. So that would be a response to the user saying thank you by saying you're welcome. And responding to a goodbye action. So this also facilitates closing a conversation. And then for our experiment, we also defined a one-dimensional baseline where we basically listed all of the combinations that we want to allow as if there were singular actions. So that will be one policy. Okay, that gives you some details about the individual policies, which I will skip. Okay, so now we are ready to set up our transfer learning experiment. So again, this is very simple in this case. So in our source scenario, or source application, if you like, we have a single request action from the task policy. It just say, oh, request a preference from the user, and this would rely on rules to decide, okay, what exactly is going to be requested. Do we want to know the preferred area or the preferred price range or food type from the user? And then if we go to the new scenario, the target scenario, we replace that request action with slot-specific request action. So now it's the policy that learns automatically what slot should be requested from the user. And then we do something similar to our one-dimensional baseline. Okay, so the experiment consists of the following steps. First, we train some policies for the source scenario. So we train a multi-policy system that gives us 4 policies, 2 of which can be transferred, the auto, feedback, and social. Then we start training policies for the target scenario. So first, we just train a multi-policy system from scratch. So that's the most difficult situation. Then also we train our single policy also from scratch. That's our baseline. And finally, we use our transfer of the domain general policies. And that's our target, our proposed system. So we train all our policies using reinforcement learning in interaction with a simulated user. And during training, we can measure different metrics like average reward, but the more interpretable metric is success rate. So that's what you're seeing here. So you see the average success rate over time during training. We see 3 curves. The green curve shows you the performance when we train everything from scratch. So that's clearly very hard. And you can see that the training is very slow. The blue curve indicates the training for our baseline system, so that in principle, if you train from scratch, is better than training a multi-policy system because it's simpler. But if we then apply our adaptation method, our transfer method, then we get the red curve. And clearly here at the beginning, at the early stages of training, you get much higher performance. And this is what matters because in practice, when you move to a new application, you don't have unlimited data. So the performance with very limited data is very important. Now, again, this is all trained in simulation. So we also wanted to see if these results can be confirmed in interaction with real people. So we kind of drew a line at a place where, for partially trained policies where both our baseline system, the blue curve, and our target system, the red curve, had sort of non-trivial performance, but showed some difference in performance as predicted by the simulation, and then sort of lined 3 systems, so our target system, the baseline, and then for reference also a fully trained policy, set these up in a human user evaluation. So that's what we did. We created a web interface that users can use to talk to our systems. We recruited them through Amazon Mechanical Turk, where we gave them instructions, and also for each dialogue that they had to do, a sort of a scenario that they had to follow. They talked to our system, and then after each dialogue, they were given a questionnaire consisting of 6 questions. The 2 main ones are shown here. So yes, no, the system recommended a restaurant that matched my constraints, or yes, no, I got all the information that I was asking for. So that gave us the following results. So you get the percentages for corresponding to the 2 questions. And what we can see here is that you get a clear improvement from the one-dimensional baseline to our multidimensional target system. For our policies that were trained on limited data. So if you would have unlimited data, you could still further improve the performance, as shown by the gray bars. In conclusion, the main takeaways I wanted to give you is that dialogue is inherently multidimensional. The multidimensional design is based on a theory in linguistics, but it's also supported by empirical evidence through extensive annotation experiments. The taxonomy, so that like the schema of all the possible dialogue acts and how it's organized, is actually part of an ISO standard, so that should stimulate interoperability as well. But the main thing to take away from our particular experiments is the transfer learning ability, so that the multidimensionality enables more efficient adaptation to new applications. And if you want to know more about the details of that research, you can find that in our paper from last year, or any other questions. I'd be happy to answer them. So with that, I want to thank you for listening.